In this video, we're going to be taking a look at logarithmic properties. This will allow us to evaluate some expressions and come up with actual answers, computational answers. More than that, it gives us a skill that allows us in the next section to solve problems involving logarithms. Now, we'll be using logarithmic properties that we introduced, but these go along with the exponent properties. So you may want to review exponent properties before you get too far into this section. Let me go ahead and share my screen with you, and we'll get started. There are a lot of logarithm properties because there are a lot of exponent properties. So we're going to kind of go along and compare the logarithmic version with the exponent version. Remember that logarithms and exponentials undo each other. They're inverse operations, like multiplication and division by the same number. So when we're looking at logarithms and the exponential version with the same base, a number that is strictly positive and not 1, we can look at the properties in both forms. The first property is one that we've talked about several times, especially when we were looking at the graphs, and that's this one right here. So we can call this one log property number 1. And it basically says, no matter what base you choose, if the power you raise it to is 0, you're going to get 1 for the answer. So in exponential form, this looks like b to the 0 equals 1. Now remember, we have restrictions on b. b has to be greater than 0 and it cannot equal 1. So let's write down again our logarithmic and our exponential forms in terms of words to help you see the relationship between the two forms of the same property. So when we write it in logarithmic form, the base goes below the word log or natural log, ln, and to the right. And then we have the answer part, which is sitting right next to it on the line. And this equals the power. Now we can compare this to the exponential form, where we take the same base, raise it to a power, and get the answer. So we can see that we have the same relationship here, and this gives us the logarithm property, log base b of 1 equals 0. In other words, if the answer part is 1, the power must be 0, all right? Or if the power is 0, the log is 0, then the answer part must be 1. The next one is another property, which is sort of related to that one. And this one says log base b of b equals 1. Now, this looks kind of weird if you put it into exponent form. So when we're comparing the logarithmic form with the exponent form, this next one is pretty obvious. It says take the base b, raise it to the power of 1, and for your answer, you'll get b. Well, that says b to the first equals b to the first, which is pretty obvious. But again, what we're seeing is the relationship between the properties in logarithmic form and in exponential form. Let's move on now to another set of properties. These are also going to be able to be written in their exponential form, and these look kind of different. These are kind of weird, all right? So the second one. The first one is pretty obvious. So this would be log property number 3. And in exponential form, what we're looking at over here is we're going to take the base b, because it is below and to the right. So that's right here. And we're going to raise it to the power x, and it's going to equal b to the x. So b raised to the x power equals b to the x. Well, similar to the last one, it's kind of obvious, right? I mean, it just makes sense. So how might you use something like this? Let's say I had log base 2 of 16 equals x. Well, this tells me that 2 to some power equals 16, but I know that 16 is a power of 2. It's 2 to the 4th. So I can rewrite this as log base 2 of 2 to the 4th. And this says, what power do I raise 2 to get 2 to the 4th? Well, the answer, of course, is going to be 4, all right? So now let's look at this next one. Number 4 is kind of weird. It it's a little hard sometimes for students to grasp. The key thing that you want to see here is that the base is b in both the exponential and the logarithm. And we have both forms here because we have b raised to a power, and that power itself is the logarithm. So we have both forms involved in this particular property. Notice also that the b and the l, the base of the exponential and the l of the logarithm in the power, are side by side. There's nothing in front. Now, what do I mean by that? An exception to that would be something like b to the 2 log base b of x. Well, then I have a problem because the 2 is between the b and the l, the b in the base of the exponential and the l of the logarithm, and this won't work for this property. If they're side by side, though, then it turns out that the b to the log base b of x is just x. Why is that? The reason is that b to a power and log base b are inverse operations. So if you multiply by 3 and then divide by 3, you haven't changed anything. So the answer part is going to be the same. And that's what's happening here. This is basically saying, if I take b and I raise it to some power x, I will get the power that I raised b to get x, right? So this one right here says, I'm raising b to some power and I'm getting x. What is that power I raised b to get that particular thing? And the answer, of course, is just x. So this gives us our result here. So again, no matter what you see, let's suppose you have log base 4 of x plus 2, and this is the power on 4 to the log base 4 of x plus 2. 4 to a power and log base 4 are inverse operations. They undo each other, and you just get what's in the answer part, which is x plus 2, right? This is a weird one. And this is one you're going to have to spend some time kind of wrapping your head around so that you can use it when you need to. Let's take a look at the next property. This next property right here, we're going to go through the proof of it because it is a more difficult one. Now this one, or actually not this one, the next one. On this one, it sort of should make sense to you. This says log base b of m equals log base b of n if and only if m equals n. Okay, well, what does that mean? Well, remember that the log is the power. So by having the logs equal to each other, I'm saying that each power is equal to each other. And it's clear that they have the same base. Well, if you take the same base and you raise it to the same power, you should get the same answer because exponentials are one-to-one functions. So if I take the same base, b, and the powers are equal, then the answers have to be equal, and that's what this is saying. If 2 of the 3 parts are the same, then the third part has to be the same as well. So it works in multiple forms. So again, you can apply this in different situations. Now let's look at the one that we have the proof for. This one and the next one are a little bit longer, a little bit more confusing. So I think this one should be property number 5 here. And this is from the one-to-one property of the logarithm and the exponent. And then this is going to be property number 6. I can't remember exactly. I think there are 8 total, right? Now, when we're looking at this one right here, what is this saying right here? And this is a very confusing one. It basically says, if there's multiplication in the answer part, what do you do with the powers? Well, if the base is the same and you have multiplication in the answer part, you add the powers, right? I mean, that's the rule. So if we're looking over here, if I had b squared times b to the 3rd, this would give me b to the 2 plus 3, which would give me b to the 5th, right? So that's the rule. This is what it looks like in exponential form here on the right, and this is what it looks like in the logarithmic form on the left. Now let's prove that this is true. So I'm going to start by looking at these 2 parts on this side right here. And I'm going to let this log base b of m be lowercase m. Now, lowercase m and uppercase m are not the same m. So I could use a a totally different letter if I wanted to. And then I'm going to let lowercase n equal the log base b of uppercase n. And again, the n's are not the same. They're not related. So this now says log base b of m times n is equal to m plus n. Now, there are different things that I can do to simplify this. And one of the things I can do is I can take this expression right here and I can rewrite it in its exponential form. So this one basically says the log base b of uppercase m equals lowercase m, which when I convert it to exponential form says b to the lowercase m equals uppercase m. So I can rewrite this logarithm using that property right there, right? So I can do different things here. I can replace m with b to the m, and then I can do a similar thing for this one. So I have, again, log base b of uppercase n is equal to lowercase n. And then if I want to convert this one into exponential, remember it's that backwards C kind of motion. The base to the power equals the answer part. So this tells me b to the lowercase n becomes uppercase n. So I can now replace uppercase n with this b to the n. So I'm going to start here on the left side, and I'm just going to replace step by step. So the first thing I'm going to do is I'm going to start with the left, which is the same as what I have here. And then I'm going to replace my m with b to the m. So now I have b to the m right here instead of uppercase m. And then I'm going to replace my n, what I see right here, with what n is equal to, which n is equal to b to the n. So now I have this b to the n. And then these are exponential, so I can use exponent rules. This one right here, which says when the bases are the same and they're both b, I can add the powers. So when I add the powers, I get this step right here, which tells me that the log base b of b to the m plus n has to be equal to log base b of uppercase m times uppercase n. And then when I'm looking at this, notice that these are the same base. So then I can use that property that I had just a minute ago, which is this one right here, property number 3, which says if the bases are the same, then the power must be the power on the answer part. The answer part is a power of the same base, then the power must be the power on the answer part. So the power on the answer part here is m plus n. So log base b of b to the m plus n just becomes m plus n. But I know what m plus n is. I have a relationship up here for m and another one up here for n. And I replace those two, which proves what I was trying to do. Now, what does that mean? I mean, how do we apply something like this? Well, this basically says if I have the log base, oh, I don't know, let's do 10 of 2xy, then this means that I can write it as the log base 10 of 2 plus log base 10 of x plus log base 10 of y. And these might make it simpler to solve and find a solution. So we're sort of stretching the problem out and making a little bit simpler. Each part is simpler. Now, if this property uses addition, what do you suppose happens when you're dividing m by? Well, what's the rule when you have exponents and you're dividing? If you have exponents and you're dividing, you subtract, and it's always the numerator power minus the denominator power. So anything that comes from the denominator is going to be negative. And that gives us our next property, which is property number 7, which for some reason it doesn't want to write. Okay, so now we're looking at property number 7 here. And when we look at property number 7, we can do the same thing we did before. We're going to let m be equal to log base b of m and lowercase n be log base b of n. And that gives us these two relationships that we had in the previous problem. B to lowercase m equals uppercase m. B to uppercase or lowercase n equals uppercase n. So we have these relationships. So I'm going to start here and I'm going to replace this uppercase m that you see here with b to the m power, and I'm going to replace the uppercase n with b to the n power. Now this gives me an exponential inside the answer part, so I'm just going to work on the exponential part. The whole thing's inside a logarithm, but inside the logarithm, I have exponentials. So I'm going to reduce the exponential. Remember the rule. If you have something that's like x to the 8th divided by x to the 4th, this becomes x to the 8 minus 4, which equals x to the 4th. I always think of it as you've got 4 on bottom, 8 on top. So the 4 on bottom cancel 4 on top, and you have 4 left over. That's sort of how I think of it. So here's the rule, b to the m minus n. But then we can apply that property number 3, which says if the answer part is a power of the same base, then the logarithm, which is the power, is equal to the power on the answer part, which is m minus n. And we get that expression there. But then we can come back over here to where we defined lowercase m and lowercase n, and we can substitute, which gives us this relationship here. So how can I apply this one? Well, let's do a natural log this time, just for fun. So let's say I have x, y, and z. All right. So my z's always look like 2, so they have bars through them, so you can tell the difference. If I'm looking at this, I can tell that x and y are multiplied together, and they're both in the numerator, so they should be positive. And the z has been divided, so it is in the denominator, which means it should be subtracted. So when I stretch this out, the first thing I'm going to do is gonna stretch apart the subtraction. So I have natural log of xy minus natural log of z. And then I can split apart the xy, and I can have natural log of x plus natural log of y minus natural log of z, right? And again, we're sort of stretching it out as long as we can make it, and we're simplifying each individual term. The whole thing is still longer, but it's less complicated than looking at it in this product and divisor form. Now we have it. 2 more properties, actually, so I guess there's 9. There are 2 more properties that we have to look at here. And the next one is one that gets used a lot. So the previous ones, actually, all of them get used a lot. So you need to be really good at all of them. The only one that doesn't get used as often is the inverse operation one. The one that says b raised to a power of log base b just gives me back the answer part. That one doesn't get used as often as the others, which is fortunate because that's the one that students have the most trouble with. All right, so let's take a look at the power rule for logarithms, and then we're going to look at why this works, right? So why this power rule works. So the rule is, let's suppose that I have an answer part which is being raised to a power, but the base in the answer part does not match the base of my logarithm. They're not the same. So this could be something like log base 5 of 9, right? So if I'm looking at log base 5 of 9, how am I going to deal with this? 9 is a power of 3, but the 3 and the 5, those aren't the same value. So the answer is not 2. In order to use property number 3, these have to match, and they don't match. So 5 raised to the second power would be 25, not 9. So I know that doesn't work. What the power rule tells us is that we can actually take this 2 and move it to the front. In other words, what it's actually doing is it's stretching the graph vertically. So it's actually a stretch of the graph. So this is equal to 2 times the log base 5 of 3, right? Now, remember earlier I said if you want to apply that inverse operation problem, you can't have something in between, but this gives us a way of getting rid of that. So watch what happens here. Let's suppose that I take something totally different. Let's say I take 6 to the 3 log base 6 of x minus 1. And I want to simplify this. So this is an expression. It's not an equation. It's an expression. And I want to simplify it. So I'm looking at this one. I can see that the base of the exponential, this is a base raised to the power 3 log base 6 of x minus 1. And the base of the logarithm is also 6. And I want to use that inverse operation property that says 6 to a power and log base 6 undo each other and just throw me back the answer part. But the problem is this 3 that you see right here is in between the 6 from the base of the exponential and the L from the logarithm, and that's not allowed. But I can take this power rule for logarithms and do it in reverse. So take that 3 and shove it back inside as a power on the answer part, x minus 1. So this then becomes 6 to the log base 6 of x minus 1 raised to the 3rd power. Now that I have that, I've got the base of the exponential 6 and the L of the logarithm side by side with no constant in between. So they undo each other. Now they have to have the same base. Both have to be 6 in this case. And then I just get the answer part. Okay, so this power rule gets used quite a bit. So you will want to make sure that you understand it. Now, why does it work? What makes this work? Let's take a look over here on the left where we have log base b of x squared. Well, x squared means x times x. So I can rewrite it in this form that you see right here on the right side in the upper row. So this gives me multiplication in the answer part. And when I have multiplication, it means I add the power. So I can split this into the log base b of x plus the log base b of x. But these are identical logarithms. So that's 2 of the log base b of x. And this is why this property works. So this property is turning out to be, what is this, number 8, I think. So we're up to property number 8. I told you there's a lot of these. So now let's take a look at the last property that we want to consider, and that's the change of base property. So when I'm looking at this one right here, this is called the change of base property. So let me write that down, change of base property. Now, why might we want to change a base property? Well, if you're looking at your calculator, there are only 2 logarithms that are on here. So I'm going to hold it up to the screen and hopefully it is clear enough. Right here under my 3rd finger, right here, you'll see that there's a log key and an ln key. And above those keys, there's an e to the x on the ln key and a 10 to the x on the log key. And what that's telling you is that there's only 2 logarithms that most calculators have on them. Some of the much newer, more powerful graphing calculators can do logs to any base, but the older calculators, the less expensive ones, the only one I expect my students to have, the scientific calculators, they only do log base 10 and log base e, the natural log. So if I have a log base 6, I need to convert it to either base 10 or base e so that I can use my calculator sometimes. So what does it look like over here? So when we're changing the base, we're almost always going to base 10 or base e. So that's the most common. And the property itself says, let's suppose I have log base 6 of, I have no idea. Let's do 37, log base 6 of 37. Now, this isn't something that I can enter in here. 37 is a prime number, so it's not a power of 6. There's no way for me to evaluate this without a calculator. I need a calculator to find a value. So when I'm looking at this one right here, what I'm going to do is change the base. So this is going to give me, let's go to log base 10 first. So I'm going to do log base 10. And this is going to give me log base 10 of the answer part and divide it by log base 10 of the base, which is 6. So the base goes on the bottom. I keep the b's together. So when you're looking at it, writing this is the same as log base 10 of 37 over log base 10 of 6. I know, I just blew your mind. Now, how do you use that to find the value of log base 6 of 37? Come to your calculator and hit the LOG key, which is automatically base 10, and then enter 37 and hit equals, and then hit divided and open parentheses, hit log again, LOG, hit 6, close the parentheses, hit equals, and I got about 2.01529 ... What does that mean? If I take 6 and raise it to this power, I get exactly 37. So let's store it in our calculator. So I'm going to store in alpha A, and then I'm going to hit 6, and I'm going to do the power key, either y to the x, x to the y, or the caret, and then I'm going to recall that power and hit equal, and it gives me exactly 37, which is pretty amazing. All right, so now I know that I've done that correctly. Right, now we could also have used the natural log key, but it would look a little bit different. So I could also have written log base 6 of 37 is equal to the natural log of 37, the answer part goes on top, and the natural log of the base, which is 6, which goes on the bottom. Now you can use parentheses as well and do it all at once. Open parentheses, natural log 37, close parentheses, divided by, open parentheses, natural log of 6, close parentheses, equals, and I get exactly the same number I got before. I got this 2.01529, etc. So I know that I can do it either way. Now I could also convert it to something that's log base 5 if I wanted to, but log base 5 isn't on my scientific calculator, so that's not much help for me, right? Now let's take a look at why this particular one works. So we're going to start with the left-hand side here. So we're going to be looking at the left side. This says b to some power is equal to the answer m. So I'm just going to let it be y. So y is equal to the log base b of m, right? So I have this expression here. And then I'm going to do something which is called exponentiating sides. So I'm going to write an exponential. So I'm going to rewrite this in its exponential form. So I have base b to the y power equals uppercase m. So then I have that property right there. So now I have an expression for uppercase m, and I'm going to come back to my properties down here, and I'm going to apply a logarithm to both sides. So we're going to apply a logarithm to both sides. Now you may be going, can I do that? Well, you can actually. This is that equality property that says if you apply a function, an operation to both sides of the equation, you won't change the solutions. Like you can multiply both sides of an equation by 2, or you could add 5 to both sides of an equation. What we're doing here is we're applying an operation, a one-to-one operation, the logarithm of some base to both sides of that exponential. So I'm actually taking this exponential and I'm going to apply some logarithm, and we're going to do base 10 just to make it more clear. So I'm doing logarithm base 10 of y, b to the y, is equal to the logarithm base 10 of m, right? So I have those two right there side by side, right? Now, what's the next thing that I'm going to do? Well, coming over here, I know that y is log base b of m, and this tells me, if I'm looking at this one right here, I'm just going to divide both sides by that log. So I can take that property, what was it, property number 8, I believe, property 8, that allows me, even though the b doesn't match the 10, I can use that property that pulls the power on the answer part to the front. So I'm going to pull the power on the answer part to the front, and this gives me y times log base 10 of b equal to log base 10 of uppercase m. And then I'm going to solve for y. I'm going to isolate y by dividing both sides by the logarithm. So I have y log base 10 of b divided by just the log base 10 of b. Now remember, log base 10 of b is not actually three things. It's one thing. It's the power. So this whole thing represents one single number. That's not three different things. It's not two different things. It's one thing, one number representing the power. So I'm going to divide both the left and the right side by that expression. And this will give me the expression for the change of base property. Oops, got ahead of myself, log base 10 of b. So this then tells me, coming over to the side, update it a little bit. I've isolated y. Don't put an equals between because they're not equal, but one follows from the other. That y is equal to the log base 10 of uppercase M divided by log base 10 of the original base b. Now, there is nothing in this problem that required it to be base 10. So it could be any base at all. It's just that our habit is to only use this when we need a calculator, and then we use base 10 or base E. I will say that most of the time we just use base E, right? The natural log. And that's mostly because we're lazy and it's less writing. So here are the two equations that you're going to use most often. Again, notice they didn't write the 10 down here, but it's understood to be 10 because they used log. This one, the base is understood to be E because they wrote ln. And both of these are going to give exactly the same result. Now let's take a look at this particular question right here. This always throws students off. They want there to be a distributive property for logarithms. There is not. There is no distributive property for logarithms. There's no distributive property for exponents. So this doesn't give you anything, all right? I mean, we can't do anything with this, right? So when we have the natural log of a sum or a difference, we're stuck. So if your answer part has a plus or minus in it and you can't factor something out and make it multiplied or divided, then that unit with the subtraction or addition is going to stay together. And there's nothing you can do about that. This does not simplify to anything. There's no distributive property for logarithms, right? Now we're going to go ahead and write down the rules for condensing logarithmic expressions. Now, earlier we used the logarithm properties to stretch it out as much as we possibly could. And then if it's stretched out, can we compress it back to one problem? And the answer is yes, of course we can. So let's suppose that I had something that looked like we'll use base 10, log base 10 of x plus log base 10 of y minus 3 log base 10 of z. Can I condense this, compress it back into a single logarithm? Because they're added and subtracted together, the answer is yes. So in order to go in reverse from stretching it out, to condense it back, we have to use the properties in the reverse order. So when we're stretching it out, the first thing we do is we split up our division, and then we split up any addition that we have, and then we pull the powers to the front. That power property acts last. So when we're condensing, it has to go first. So that means that this 2 has to come back up on top of the x, and this 3 has to come back up on top of the z. Now you can leave the negative in between, or you could actually pull it into the power. It gives you the same result either way. So in looking at this, this is going to give me log base 10 of x squared plus log base 10 of y minus log base 10 of z. Now, some of you might have rewritten the last term only as plus log base 10 of z to the negative 3. And I forgot my 3, didn't I? I said it, but I forgot to write it. You can do either one of these. They're both correct, and I'll show you why they lead to the same thing. So if I have this expression right here, the next thing I want to condense is any additions. I want to put my additions together. basically any things that share the same sign are multiplied together. So if I had two negatives, those two negative answer parts need to be multiplied together, and the two positive answer parts need to be multiplied together. So this becomes log base 10 of x squared times y minus log base 10 of z to the third. Or if you had done it the other way, over here, you would have log base 10 of x squared y z to the negative 3, because they're all positive, so they're all multiplied together. Now, if I'm looking back at the one on the left, I've got subtraction, a positive logarithm base 10 and a negative logarithm base 10. They all have to be base 10 or you can't do this. This means that I've got division. So the positive ones move to the numerator of the answer part. So this becomes x squared y. And the negative one moves to the denominator of the answer part. Now, you may say, well, that doesn't look like the blue one, but it actually is, because remember that when you have a negative exponent, it's a position changer. It's in the numerator, it moves it to the denominator. If it's in the denominator, it moves it to the numerator. So this actually can be rewritten with an answer part of x squared y divided by z to the positive 3. When you change the position, the exponent changes sign. And you can tell that these are, in fact, equal. So we've talked about all of the properties, and we've talked about how to stretch one out so that it's in this longer form that you see up here at the top. And we've talked about how to condense them and how those properties have to be applied in reverse order, and how there's sometimes different ways to interpret it, but it does lead to the same result. So at this point, we're ready to turn our attention to the homework problems and take a look at those. So let's take a look at problem number 1. We are asked to expand natural log of quantity 14xy to rewrite as a sum, difference, or product of logarithms. In other words, they want us to stretch it out as much as we can. Expand, stretch out, simplify, different ways of writing that. So I'm going to have the natural log. The base is e, even though it's not written because we have ln. And the answer part is 14xy. Now, this is not an equation. This is an expression. So what I'm going to do is I'm going to simplify each part of it by writing it as the sum of different logarithms. So they're all going to be base e. And I have basically two multiplication dots in there, one between the 14 and the x, one between the x and the y. So that will give me 3 terms when I stretch it out. So I have natural log of 14 plus, because they were multiplied, natural log of x plus natural log of y. None of these have powers on the answer part, so there's no power property to apply here. And then we just come over here and we find the one that looks like that, which looks like problem number B. Okay, let's move on to the next problem, which is very similar. It asks us to expand the logarithm as much as possible, writing it as a sum, difference, or product of logs. So when we take the natural log of 19 divided by x, keep in mind that if you're using line notebook paper, the bottom of the x is on the line. It is not below the line. It's not part of the base. So it sits even with the ln. This is division. So this is going to split up into a difference. So the one from the numerator becomes positive, and the one from the denominator becomes negative. So we have natural log of 19 minus the natural log of x. Let's expand this one now. Now this one is the natural log of 1 over 4 to the k. So this one we may have to do a little more work because part of that answer part has a power on it. So we have the natural log of 1 over 4 to the k. Now we know that we have division, which is going to split up as a difference. So the numerator becomes the positive natural log. So we have natural log of 1 minus the natural log of 4 to the k. Now, the very first property we had was if the answer part is 1, then the power was 0. So if you have a 1 for the answer part, this becomes 0. So I have 0 minus the natural log of 4 to the k. I'm not done yet because there's also a property that says if these bases do not match, and they don't, this is base E, this is 4, I can still take the power on the 4 and pull it to the front. So this is going to give me negative k natural log of 4. All right, so negative k natural log of 4. Basically, we have 2 powers, so we multiply the powers together. That's what this is doing. We have 2 powers. The natural log is a power and the k is a power, so we're multiplying the powers together. 1 base, 2 powers, you multiply the powers. So coming over here, it looks like problem or selection D. Now, there is actually something else you can do here, which the problem doesn't do. And I want to point this out so that you can start seeing ways to simplify things on your own. And that is that 4 is actually a power of 2, right? It's 2 squared. So I could write this as minus k, the natural log of 2 to the second power. Now, the base is still e, so e and 2 don't match. But this is also a power on the answer part. Can I pull that to the front too? The answer is yes. Yes, you can. So this becomes minus 2k, the natural log of 2, which of course is an answer choice, but so they weren't intending for you to do that. But this is as simple as you can make this particular problem. This is as simple as it gets. Let's move on to problem number 4. This time we're looking again to expand, but we've got more involved answer part here. So we've got x to the 4th times y to the 5th divided by z to the 5th. So I know the x thing will be positive, the y thing will be positive, the z thing will be in a negative logarithm because it's coming from the denominator. Now, I don't like the way they've written it here. It really should be written, and there's no base written, so it should be 10. It should be that the answer part, the bottom of the answer part, reaches the bottom of the line where the log sits. So the z to the 5th should actually be even with the log. If you're going to write it out, you need to write it out the correct way. Don't get those answer parts creeping down to where the base belongs. So when I'm looking at this, they're all base 10. So I'm going to split up first the division. So this is going to give me log base 10 times x to the 4th, y to the 5th, minus log base 10, z to the 5th, right? Then I'm going to split apart anything that is multiplied together. So this is going to become log base 10 of x to the 4th plus log base 10 of y to the 5th minus log base 10 of z to the 5th, right? Just better to go ahead and write the base 10. I'm still not done. The last property you apply in expanding is to pull any power on the answer part to the front. So I'm going to pull the 4 to the front. So I get 4 log base 10 of x plus 5 log base 10 of y minus 5 log base 10 of z. And that's as much as you can expand it. Now, I want to do another problem here before we move on. What if this had instead been the natural log of x to the 3rd over y squared z squared, all right? Instead of having 2 factors in the numerator, I have 2 factors in the denominator. What's going to happen, and again, you take care of the division first. So this is natural log of x cubed minus the natural log of y squared times z squared. Now, when we're doing this, note that both of these have the negative sign on them, and that's going to stay. They need to be split up, but they're both going to be negative because they came from the denominator. You can also think of it as distributing the negative across the natural log. So the natural log itself becomes y squared plus natural log of z squared. And then you have to distribute the negative over both terms. So you get the natural log of x cubed minus the natural log of y squared minus the natural log of z squared. The easier way to think of it is anything coming from the denominator is going to have a negative, because in the denominator, the exponent would have been negative if you'd moved it. And anything coming from the numerator is going to be positive. And then the last thing we want to do is rewrite it by pulling the powers to the front. So we would get 3 natural log of x minus 2 natural log of y minus 2 natural log of z. Let's move on to another problem. We're going to be looking at a very similar one to what we just did last time. And I'm going to show you a couple of ways of approaching this. There's no one right way. So when we're looking at this, I'm going to show you first the straightforward, and then I'm going to back up and show you something that might make it easier. So we have b to the negative 3, c to the 4th, right? So in time, you may actually be able to skip steps and write things out more quickly, but we're going to keep going and doing one step at a time. So first, we're going to pull apart the division. So we have log base 10 of a squared minus log base 10 of b to the negative 3 c to the 4th. And then again, these two that we see over here in the right term are multiplied together. So that's going to become addition, but I have a negative here, so it's going to distribute across my addition. So I have log of a squared minus log of b to the negative 3 plus log of c to the 4th. And then the next thing I'm going to do is distribute the negative. So I have log of a squared minus log of b to the negative 3 minus log of c to the 4th. And then the last property I apply is the power rule, which brings the power to the front. So this becomes 2 log base 10 of a. Notice the negative 3 multiplies by the negative and actually gives me a positive. And I'll show you in a second why that ended up positive and not negative, even though it came from the denominator. And then the last term becomes minus 4 log base 10 of c. If I start back over at the original, back up here at the top, notice that I have a negative exponent on part of the answer part. I have this b to the negative 3. If I want to, I can rewrite it by moving that b to the negative 3 to the numerator, and that will change the sign to be positive. And then I would have log of a squared times b cubed over c to the 4th. And this then would split up, and I would have log of a squared b to the 3rd minus log of c to the 4th. Then I would split up the a squared and b cubed. Since they're multiplied, it becomes addition. And so this becomes log of a squared plus log of b cubed, and then minus log of c to the 4th. And finally, I would bring the powers to the front, and I would end up with the same exact result I got when I did it in blue. Right? So again, a different way of looking at the problem, but coming up with exactly the same result. All right, let's do another problem where we are stretching these out as much as we possibly can. Okay, so if I'm looking at this one, I want to use the properties of logarithms to expand it as much as I can. And notice I've got this 5th root in here, which we're going to have to talk about how to deal with that. So we actually already know how to deal with those because we know what a 5th root does. So we're going to first rewrite it in a better form. So I have base 10, even though it's not written, I can write it. I have x to the 8th, y to the 7th, And then I have this fifth root of x cubed y to the sixth. All right, now there are different ways of handling this. And again, there's no one right way, but I'm going to show you what I consider to be the simpler way, the more straightforward way. And that is, first off, I'm going to look at this answer part and see if I can simplify it. I need to rewrite the fifth root as the 1/5 power. So this becomes log base 10 of x to the 8th, y to the 7th, times, and I've got both x cubed and y to the 6th being raised to the 1/5 power. And all of that is inside the answer part being multiplied by x to the 8th, y to the 7th. Now I've got inside of the square brackets, x cubed, y to the 6th, which have two powers on them. X has a third power and a 1/5 power. So the rule is when you have two powers on the same base, you multiply the powers. So in the next step, I'm going to simplify a little bit further, which is going to give me x to the 8th, y to the 7th, times x to the 3/5 times y to the 6/5, right? Those are powers, okay? Now, looking at this, I see that I've got two x factors and two y factors, and then I can think about what the rule is for that. So the rule is when the base is the same, you add the powers. So I have x to the 8 plus 3/5, and this becomes times y to the 7 plus 6/5. Right? Now, we can go ahead and use fractions to find the values of those, or we can wait a minute and find it out in just a second. We will need to find the fraction for that. So let's go ahead and do it on the side. We have 8 plus 3/5. This is 8/1. So we multiply by 5/5, which gives me 40/5 plus 3/5, which becomes 43/5. Right? And on the y, I had 7 plus 6/5, and I'm going to multiply the 7/1 by 5/5, which is just a form of 1. So I'm changing the way the number looks, but I'm not changing the decimal value of it. And this is going to give me 35/5 plus 6/5, which gives me 41/5. So coming back over here, I have new powers. These are multiplied together, so I can split it up into a sum. So I have log base 10 of x to the 43/5 power, and I'm going to have to write sideways because I'm running out of room, plus log base 10 of y to the 41/5 power. And then the last thing we do is bring the power to the front. And so when we bring the power to the front, I'm going to have 43/5 times the log base 10 of x plus 41/5 times the log base 10 of y. Now, is there another way to do it? Absolutely, of course there is. You could have converted the fifth root into the 1/5 power, and then you could have left it in this form right here that we're looking at right here. And you could have split each of those up into 4 different things. But when you bring the powers to the front, you're going to get 2 log base 10 of x terms with different coefficients. So you'll have to combine the coefficients to come up with the final result. You'll get the same answer. It's just a different process, different way of looking at it. Let's now take a look at something that goes in the opposite direction. So instead of trying to stretch things out, let's compress things back together. So first off, in order to compress, they all have to have the same base. If they don't have the same base, you can't compress them. So if I have, for example, a log base 2 of x plus a log base 3 of y, then that's what I have. I can't do anything with it because this is a 2 and this is a 3. They have to have the same base. So over here, this doesn't have the base written, but we can assume the base is 10. So we have log base 10, and this is going to be log base 10 here. So it's stretched out. I want to compress it back. So remember, we go in the reverse order. So the last thing we do in stretching out is bring the powers to the front. So if we had a power on the front, we'd push it back inside, but all of our coefficients are positive ones. We don't have to worry about that. And then the next thing we would take care of is we would contract any addition into products in the answer part. And we do have that. So this is going to become the log base 10 of 9 times x times y. And that actually is as far as I can go because there's not a subtraction. And that's it. That's all I have to do. So this is just a way of contracting it back into a single logarithm, right? Now let's do the same thing for this one here. In this particular problem, we want to take a look at it again. We want to see what the bases are first to decide if they're the same. This is log base 10, log base 10, log base 10. And when I contract it, I want it to be log base 10. Now, I look first to see if there are any coefficients at the front of the log other than a 1 or a negative 1. And I do not have anything other than 1 or negative 1. So the next thing I'm going to do is I'm going to contract anything that had addition in it into a product, and anything with subtraction is going to go into a division. So when we're looking at these, the thing that you're actually doing is you're factoring out the minus from the last two terms first, so that you have log base 10 of b plus log base 10 of c. And then you're going to contract those into multiplication. And this becomes log base 10 of b times c. And then you have just the one subtraction. And subtraction, you know, converts as division. Anything that's positive was in the original numerator in the compressed or condensed form. And anything that was from a negative logarithm goes to the denominator. So you have log base 10 of a divided by bc. Now you can also do that directly from here if you have already taken care of pushing any constant coefficients back inside as powers on the answer part. Then anything that has a negative is going to end up in the denominator. And anything that is positive is going to end up in the numerator, so you can get the same result. Let's take a look at this problem. So in this problem, it wants us to condense the expression to a single logarithm. Notice that this is not actually expanded as much as it could be, right? There's more we could do here. There is multiplication inside of each of these, so we could stretch it out more. So I'm first going to show you what it would look like fully stretched out. So this would be natural log of 8 plus natural log of x to the 9th. And then because this has a minus here, both of these are going to be minus when you stretch it out. Natural log of 7 minus the natural log of x to the 6th. Still not fully stretched out because you have two answer parts with a power on them, which could be brought to the front. So you have natural log of 8 plus 9 natural log of x minus the natural log of 7 minus 6 natural log of x. Now that's fully stretched out. Regardless, we're going to start from this one right here. I've got two natural logs, so the base of both is e. The only coefficients are 1 and negative 1, so I don't need to push a power back inside. And I don't have any addition, so I'm just going to condense the subtraction into a ratio. So this is going to give me 1 natural log, base still e, and then the numerator is going to come from a positive logarithm, 8x to the 9th, and the denominator is going to come from the negative logarithm, 7x to the 6th, all right? Now you may look at that and go, yeah, but that's an exponential and I can simplify that. Yeah, and you should. So the next thing you're going to do is you're going to write natural log. Now you can't reduce the 8 over 7, but 9 and 6 are both divisible by 3. So this gives me 8x cubed divided by 7x squared, right? And then, well, actually, we could have done something a little bit better. Let's back up and do it the other way, which is just saying I've got 9 on top and 6 on bottom. The way I just did it does not work, so don't do that. So we're going to look at this one and we're going to divide it, and we have 9 on top, 6 on bottom, and that will give us 8/7 x to the third, right? And that's the final answer. Okay, let's take a look at this one. Again, we want to condense into a single logarithm. So first we look to see that they all have the same base. They're all base 2. So I can condense them into a single logarithm. Next, I look to see if they have a coefficient other than +1 or -1. And 2 of the terms do. So my first step is to push those back inside. So I have log base 2 of x, which had a 1 coefficient, so it stays the same. The second term had a +3 coefficient, so it becomes log base 2 of y to the third power. The 3 at the front becomes a power on the answer part. Now I'm only going to move the 4 because I like to leave the negatives out front. So on the last term, it's going to stay minus, and then it's going to be log base 2 of z to the 4th. If you move the negative, then it becomes a positive, and you can do it that way. That's also correct. All right, so when you're looking at this, this is the next you've gotten to. Notice that I have 2 logarithms here on the first and the second that are positive, and 1 logarithm that is negative. They're all log base 2, so that's going to stay the same. And then I'm going to have x times y cubed in the numerator and z to the 4th in the denominator. And this is as condensed as you can make it. Okay, let's take a look at number 11. Number 11 is very similar. And number 11, we are also condensing it. So let's go ahead and pause the video, work this one out, and then turn the video back on and we'll compare our answers. So how did you do? You may have gotten stuck partway in this one because this one uses a property that we haven't used before, the one-to-one property of logarithms. On this particular problem, you actually have 4 logarithms, and this is not an expression, it's an equation because you have an equals and something on both sides. They're all log base 10, so we know we can compress them. Now, it helps to know what it is you're looking for, and we're looking for a. So I'm going to leave the log base 10 of a alone and leave it where it is. Now, the next thing that I'm going to do is I'm going to look at this right here, and I'm going to compress the left-hand side. So the first thing I did was notice that the middle one had a coefficient of -1/2, -1/2, and the third one had a coefficient of 5. So the first thing I did was push those back inside as powers on the answer part. Then I had 2 positive terms here, the log base 10 of x and the log base 10 of z to the 5th. So both of those answer parts became factors in the new answer part. The one that was negative went to the denominator. So then I had log base 10 of xz to the 5th over y to the 1/2 equals log base 10 of a. Now, there was a property that says if the logs are equal, then what we're saying is the powers are the same because the log is the power. And they both have base 10, so the bases are equal, and that's 2 out of the 3 parts. There's a base, a power, and an answer part. And we know that the powers are equal and the bases are equal. If you take the same base to the same power, I should get the same answer because exponentials are one-to-one functions. So that means these answer parts have to be equal. If the 2 answer parts are equal, I can set them equal to each other, and that gives me A. Now, let's back up and look at it from a different standpoint. Some of you may have actually approached this differently, where you moved all the logarithms to one side and then condensed that side. Let's see if that gives the same result. And of course, you know the answer should be yes. But let's go ahead and take a look at that now. So we're going to start back with the original problem. So we have log of base 10 of x minus, and I'm going to push the 1/2 back inside. And again, the 1/2 power is also the square root. So if you want to write it as the square root of y, you can do that from the beginning. And then this becomes log base 10 of z to the 5th. And then if I want to, I can subtract the log base 10 of a. So I have minus log, oops, I cursed it, which I only do for natural log base 10 of a. But I didn't lose the other side of the equation. It's still there. It's just now 0. But don't lose that equals 0. It's important. We're going to need that. So now when I'm looking at this, I actually have 2 that are positive and 2 that are negative. So the 2 that are positive are going to have their answer parts become factors in the numerator, and the 2 that are negative will have their answer parts become factors in the denominator. Notice that all of the coefficients are now either 1 or -1, and they're all log base 10. So I can condense them together. So I have log base 10. X was positive from a positive logarithm, so it goes on top. And the y to the 1/2 came from a negative logarithm, and I'm going to write it as square root of y. The log of z to the 5th was positive, so z to the 5th goes on top. My x is kind of moved over too far. There we go. And then the log base 10 of a was negative, so the a goes to the denominator, and it equals 0. Now you may look at that and go, that is not what you got the first time. I'm not done yet. I need to solve for a. And when you're looking at it, and sometimes, a lot of times, you get to this point, and you're like, well, I don't know what to do next. Well, I'm in log form. If you can't think of anything else to do, switch to exponential. So that often helps. If you're in log form, switch to exponential. If you're in exponential, switch to log. See if that helps. So then I'm going to rewrite this one. And this is going to give me 10, the base, being raised to a power, giving me this for the answer. So I have 10 to the 0th power equals x z to the 5th divided by the square root of y times a. Now, what is 10 to the 0th power? Well, any value to the 0th power except 0, we cannot take 0 to the 0th. Any number to the 0th power is 1 except 0. 0 to the 0th does not exist. So then this gives us 1 on the left equal to xz to the 5th over the square root of y times a, and I can multiply both sides of the equation by a, and that will let me solve for a, and this gives me that a is equal to xz to the 5th divided by the square root of y, which is the same thing I got in the first method. So they are equivalent. They will give you the same result. Let's now turn our attention to problem number 12. Problem number 12 is using one of the properties we've not used yet. This is the change of base. And again, we mostly use this when we can't simplify it to get to a number value by switching to exponential form. And we need to convert from one base into something we can do on our calculator. So for example, looking at this one, there are 2 problems, part A and part B. So part A is log base 5 of 2. And we want to know what that is equal to, what number that equals. So we want to be able to use our calculator. And in order to use our calculator, we either have to use log base 10 or natural log. So we'll convert it to both. Remember, when you convert, this becomes, we'll do log base 10 first, log base 10 of the original answer part divided by log base 10 of the original base, which was 5, right? So this is one possibility, log of 2 divided by log of 5, which looks like it's right there, right? Now, we also could have switched to natural log. If we'd switched to natural log, it would be natural log of the original answer part divided by natural log of the original base. Always make sure that you keep it that way. It looks to me like we've got more than one possibility here. Oh, except it says use base E. So if we want to use base E, then we're looking for this one right here. But in actuality, this one also works as well and will work on your calculator. Let's look at this one. Now, this one wants us to change to a ratio of logs base 6, which we would not often do because I don't have base 6 on my calculator, but we can do it. That means it's not going to be a problem. So we have log base 8 of 14. So the original answer part's 14 and the original base is 8. So we're going to convert to log base 6. So we're going to have a log base 6 in the numerator and the denominator. And in the numerator, it's log base 6 of the original answer part, which is 14. And in the denominator, it's log base 6 of the original base, which is 8. And it looks like that would be option number C, right? And again, we could also convert to log base 10 or natural log. Let's move on to our last problem here. And the last problem, we want to use these properties of logarithms to see if we can actually simplify to a value. If you have to use the change of base formula, then generally you can't. You need a calculator. But there are lots of occasions where we can simplify these and actually come up with numbers instead of the logarithm expression. So I'm looking at this one right here. It's very complicated, all right? It looks, well, it just looks really awful. So the first thing I'm going to do is I'm going to look at the individual pieces a little bit. So I'm going to break it down by looking at each individual piece. Now, there are lots of properties you can apply. You can apply them in all different orders and still come up with the same answer. The first thing I see, though, is this part right here. Log base 4 of 4. Well, what is the log base 4 of 4? 4 to what power gives me 4? 1. So this part highlighted in yellow just becomes 1. So this becomes 2 times 1, which is 2. So this problem right now has now simplified to 2 plus the log base 4 of 64 divided by 3 times the log base 9 of 729. Right? Now, notice I did not push the 2 inside. You can, that's okay. That would have given me log base 4 of 4 squared, which is 16, and 16 is 4 squared. I still would have gotten a 2. The problem is if you push it inside, it makes the answer part larger. And we're trying to make it simpler. Making the answer part a bigger number is probably going to make it more complicated. So it's usually better to simplify the answer part with the coefficient left outside if possible, right? So now let's take a look at log base 4 of 64. So I'm going to isolate the numerator of the second term. So I have log base 4 of 64. Well, I don't have a coefficient this time other than 1. But the question is, can I write 64 as a power of 4? It's a power of 2, but is it also a power of 4? And the answer is yes. So it super helps to know your common powers. And I'll make a list after this problem of all the powers you ought to know. So this becomes, of course, log base 4 of 4 to the third, which basically says 4 raised to some power gives me 4 to the third. So this just simplifies to 3. So now I can replace this part over here. And this part becomes 2 plus 3 divided by, oops, my bar got too far. 3 divided by 3 over log base 9 of 729. Now you may go, ooh, can I cancel those 3's? Well, actually you can, because this is a 3 times the logarithm. So it is a factor. So you can cancel the 3. Could you cancel the 3 and the 9? No. Everything inside the logarithm is part of one number. Log base 9 of 729 is one number. It's log base 9/7 of 29. It's one number, all right? Don't think of it as three separate things. It's one thing. We could cancel this. It does not let the logarithm jump to the numerator. We're still going to have 2 plus 1 divided by log base 9 of 729. Now, when we're looking at this, and you're looking at that last expression and you're thinking, oh gosh, I don't really know how that simplifies. So we'll pull it out to the side. The chances are high, says it said without using a calculator, that 729 must be a power of 9. All right, so how are we going to figure that out? So we're going to come over here and we're going to do a shorthand division. You've never learned this. It's really great. You'll enjoy this. So we're going to do the division bar upside down like this, and we're going to divide by 9. 9 goes into 72 8 times with 0 left over. If I had something left over, I would put it in front of the next digit. 9 goes into 9 1 time. So now I have an 81, and actually I should have written that below. And then I can do it again, right? So it's freezing on me here, so I need to save it for a second, right? And then I can do the division by 9 again. So then I divide by 9 again. 9 goes into 81 and leaves 9. 729 must be 9 to the third. So this becomes log base 9 of 9 to the third, which says 9 to the third power gives me 9 to the third. So log base 9 of 9 to the third is 3. So this is going to then give me, coming over here, 2 plus 1 divided by 3. Now I need a common denominator. And so I'm going to write the 2 as 2 over 1, and I'm going to multiply by 3 over 3, which gives me 6/3. So I have 6/3 plus 1/3, which gives me 7/3. And that would be our final answer. So we've gone from something that was super, super complicated and nasty looking up here to a single number. And we can use the properties of logarithms in order to do that. Now, I said I would give you some powers that you need to know that will really make your life easier. Basically, you need to know all the powers of 2. So 2 squared is 4, 3 squared is 9, 4 squared is 16. Let's go ahead and just write all of these out really quickly. That would be 36. 7 squared gives me 49. 8 squared gives me 64. 9 squared gives me 81. 10 squared gives me 100. No, you should not stop there. You should keep going. 11 squared you need to know is 121. And 12 squared you need to know is 144. That's probably enough. I know a few more, but that's probably enough. I'll show you on the side the ones that I think are bonus ones to know. When we're talking about third powers, we need to know that 2 to the third gives me 8. 3 to the third gives me 27. 4 to the third gives me 64. And 5 to the third gives me 125. That's usually enough for the powers of 3. What about powers of 4? You need to know 2 to the 4th is 16. And 3 to the 4th is 81. You need to know those at least. And then you probably don't need to know the others. I do actually know 5 to the 4th is 625 because I think of it as 25 quarters, which will give me $6.25. So that's the way I remember 5 to the 4th. You do need to know 2 to the 5th, which is 32, and 2 to the 6th, which is 64. So notice that 64 actually shows up here several times on our list, right? So it shows up more than once. So it's definitely one that we want to have. And 16 shows up a couple of times as well. It's both 2 to the 4th and 4 squared, right? So these are powers that you definitely ought to know. Some that are nice to know would be 13 squared is 169 and 14 squared is 196. You just reverse the latter two digits. And then 15 squared is 225. And like I said, 25 squared is 625, but because 25 is 5 squared, 5 squared squared is 5 to the 4th. And that's, of course, also 625. So that becomes a nice one to know as well. In our last video, we'll be looking at actually solving equations. So we'll be doing more like the problem where we solve for A, where we're solving equations. And those can be a little bit trickier because we can get what are called false solutions or extraneous solutions. I hope you'll join me for the last section on our study of logarithms and exponentials.